They're onto me. I can feel it in my gut. So, just to be safe,
I armed myself to be ready to defend us.
Anyway, in part 1, we got our kernel up and running. Now, we're going to implement serial communication. And if you think that's boring, you're wrong! By the end of this video, we will have the foundation to control our kernel remotely, meaning we will be able to send output like logs to another machine. And we will be able to receive input, like something we typed into another machine's console. But there's more! This knowledge gives us the ability to access the kernel of almost any IoT device. And we'll see exactly how that works when we connect to this router. Let's go! Okay, we add serial in and output to our kernel. And specifically, we implement UART. But first, let's clarify what serial communication is. Well, at the most basic level, it's a way to transfer data from one location to another. Alright, let's take a closer look. Usually, we have a transmitter, so a place from where we send data, and a receiver, a place where the data is, well, received. And these two places are connected by a line. So all of this is fairly abstract. And when I learn about stuff like this, it helps me tremendously to see what this looks like in the real world. So let me show you. A line could be a wire like this jumper cable. And in fact, we'll use jumper cables like this later to access the router's kernel. But a line could also be something different, like on a chip where we obviously have way smaller wires that are etched into the chip itself. But in practice, it's pretty much the same. Now, sending data, let's say a bit, means nothing more than applying a voltage on the transmitter side for a given amount of time and then measuring that on the receiver side. But let's save the details on that for later and get back to what serial means. So, the word serial in serial communication means that we send each bit separately. So if we send a byte, that is 8 bits, we send it, well, in a series over one line. And that's where the name serial comes from. Yeah. Who could have guessed that? And as a side note, of course, serial communication is not the only way of transferring data from A to B. So let's briefly contrast serial with its opposite, if you will, which is parallel communication. And in parallel, we send all the bits of a byte simultaneously. What's important for us right now is only to know that these ways of transferring data exist and that they obviously require different rules on how we send and receive data. Now, serial communication itself is a large area with lots of different standards, and that is rules on how to communicate. And we focus now on UART, which is one of the simplest. And UART is also the one that enables us to use a device like this to get a shell on the router. So, how does UART work? Let's say we send something like this over the line. So we apply a high voltage over some time, and we apply a low voltage over some time, and so on. And then this is what the receiver measures. So what is this? This could be anything. Okay, first let's agree on that a high voltage means 1 and that a low voltage means 0. Good. Now this has some meaning, but there's a problem. This part could be a single one, or it could be 4 ones. It could be 50 ones. We just don't know. And we don't know because we have no rule on how to separate the single data points yet. So, what we have to do is to agree on a fixed period of time that tells us how long a signal has to last to count as a single data point. And in UART, this time length is defined by the so-called baud rate. And the baud rate is defined as the number of symbols, or you might also say data points, that are transmitted in 1 second. Alright, for our example, let's choose a random baud rate of say 16. and that is 16 signals per second. And let's also say that this whole transmission lasted for 1 second. Now, if we apply our baud rate of 16 here, we can derive our binary message from this separation. And that is because the whole signal is 1 second long. And with a baud rate of 16, there are 16 data points in a second. And now we are able to translate the whole thing to binary. So let's try another baud rate. And this time, let's choose 8. And if we do the whole thing again, we get this in binary. So you get the point. Okay, so the thing is, we have to choose a baud rate, and the baud rate should be the same for the sender and for the receiver. And of course, real baud rates are way larger, because 8 bits per second is, a little slow. And here we have some common baud rates. And that's quite important to keep in mind for later, because to access the router, we have to guess its baud rate. Okay then, we're finally ready to start implementing. Alright, this part is probably the most tedious of all. So stay strong and bear with me. Now, this is where we left off in part 1. Setting up the serial ports is quite similar to how we changed the cursor style and the cursor position. And that is, we write specific values to specific registers using the out instruction. Okay then. The initial config of the serial COM is very much like following a recipe. And we can find the recipe here in the OSDev wiki. And this wiki is one of my main resources to acquire knowledge. The only downside is that it from time to time has a little gatekeepy rhetoric in it. So when it says that you need to have at least 80 years of C experience and a 99.999% genetic overlap with Dennis Ritchie to start developing your own kernel, you can safely ignore that. Anyway, back to serial. First, we define constants for the base addresses of COM1 and COM2, which are shown here. And next, we also define all the register addresses shown here. And if we write these down explicitly, we get this. And just like with the CRT controller from part 1, all of these registers can be used to control different aspects of the serial connection. But let's not go into details until we actually use them. Alright, let's switch to C and implement the constants. Okay, we create a new header file and then we define the constants. And let's keep the register constants dynamic such that we can use them for all the base addresses that we have. As a first step of the config, we deactivate interrupts. Activating interrupts would mean that the UART controller interrupts the CPU each time when its buffer is full. And because we have not implemented interrupt handling yet, we don't want that. Instead, we use a polling approach. And that means that we have to proactively ask the UART controller what its state is. And we'll see later what that means in practice. Now, to deactivate interrupts, we only have to set the interrupt register to 0. And to do this, we use the out instruction as we did in part 1. As a second step of the config, we set the baud rate. And to do this, we have to follow these steps. And the first thing to notice is that we do not set the baud rate itself, but a divisor. The baud rate we set is calculated by dividing a base rate of 115,200 by the divisor. If we choose, for example, a divisor of 2, our baud rate would be 57,600. We, however, choose a divisor of 1 such that we get a baud rate of 115,200. Now, to set the baud rate, we have to do the following. First, we have to set the most significant bit of the line control register to 1. This activates a kind of switch for the data and the interrupt register. And when activated, they accept our divisor instead of serving the original purpose. Now we have to send the divisor's least significant byte to the data register and the divisor's most significant byte to the interrupt register. And that's it. Alright, let's implement that in C. And again, we use the out instruction to write the values we just talked about. Third step, we configure the UART frame. But first, we must understand what a UART frame is. So in UART, data is sent in specifically defined chunks. And these chunks are called frames. And each frame consists of the data that is sent and 3 or 4 additional control bits. Depending on the config, the data is between 5 and 9 bits long. Then, the remaining config bits are a start bit that signals the receiver by a falling edge that data is coming in, a stop bit that signals the end of the frame, and depending on the config, this can also be 2 stop bits, and finally, an optional parity bit that serves as a kind of simple checksum. Alright, we choose a very common frame layout called 8 none 1, which means that we have 8 data bits, no parity, and 1 stop bit. And to configure that, we have to set the line control register to a specific value. And here we see what this value has to be. So we set both bit 0 and bit 1 to 1, then bit 2 to 0, next bits 3 to 5 to 0, and finally bit 6 and 7 to 0. So we get this value in binary, which converted to hex is this. And implementing that in C is quite simple. We just have to use the out instruction to set the value. Now, as a quick last step, we configure the FIFO buffer and the flow control. And right now, we don't do it properly, just so we can use the connection. And in fact, this will cause a minor issue as we see later, but nothing dramatic, and we'll fix that in the future. So we activate and flush the buffer like this, and by doing this, we set the modem control register so that it signals that the device is ready to transmit. And now finally, we're done with the config. Okay, let's take a little detour and take a look at how UART is used today. Because you might think that because UART is a pretty old technology from the 70s, it's not used in today's devices. But quite the opposite is true. It's, for example, widely used in IoT devices because it gives the engineers who built these devices an easy way to get logs or a shell. And because they can access it, we can too. So to see how that works, we take a look at a cheap router.
Quiet. There it is, peacefully sitting with a quiet grace and utterly unaware of our presence. Let's open it up and see what's inside.
Alright, so our goal is to access the router's kernel through its UART connection. So let's see where it is. But first, to be able to find it, we must know what to look for. So earlier, we already talked about the transmitter and receiver in the serial connection. But only having that between 2 devices would just enable us to send data in one direction, and that's not what we want. So when we have 2 devices, both must be able to send and receive data. And to do that, we use 2 lines. One line that sends data from here to here, so we need a transmitter here and a receiver here, and another line that sends data from here to here. So we also need a transmitter here and a receiver here. Then both lines share a common ground, and this serves as a way to provide a voltage reference point so that the signal levels can be interpreted correctly. And then there's the VCC. And I wouldn't touch that unless you know what you're doing, because it carries a supply voltage which could, if you're using it wrong, fry your device. So just be careful. Anyway, now we have what a UART connection looks like. And that's exactly what we have to look for. A group of 3 to 4 pads or pin headers on the PCB. And sometimes the vendor makes it real easy by labeling them. And lucky us, that's the case with this router. See, here we have the labels that belong to UART. TX, RX, ground, and VCC. Okay. Let's step back from the router for a second, because we still have some work to do on the kernel. And what we're going to do now is to implement some serial I/O functions. And I tell you, I really like how that turned out. Alright, first we implement serial output. And what that means is that a kernel can send data to some other device via UART. For example, it can send text to the terminal of another machine. Okay then, let's implement that in C. But first, let's put the setup in a dedicated function. So we create a C file for all of our serial functions. Then we create a setup function which takes a serial port as an argument, and now we just copy the setup code we've written before. And let's not forget to add the function declaration to the header file and to call the function from kernel main. Okay then. So to output something, we first have to ask whether the connection is ready to send. And to do this, we use the line status register. And this register contains various pieces of information about the connection status. And to get this information, we simply have to use the in instruction. And then we have to filter out the value we are interested in. And right now, we want to know whether the transmission buffer is empty. So we have to check whether bit 5 of the register is set to 1. So we write a simple if statement to check that, and then, if the connection is ready to send, we can start the transmission. And to do that, we only have to write the value we want to send to the data register. And we do that, as always, by using the out instruction. Okay. Let's test that in our emulator. And we have different options to do that. For example, we can let QEMU put the output into a file. So let's try that. Okay, works great. Or we can let it put the output into our terminal. So let's try that too. And this also looks great. Okay, this already is really nice, I think. Because as we see later with the router, if our kernel were on a real machine, we would now be able to send, for example, some logs to a serial terminal. But to be honest, the serial input we implement in a minute is way cooler. But first, let's put the output into a function. And to do that, we first write a function that tests whether the connection is ready to send, and then we write the send function itself. And let's also briefly write a function that is able to send an entire string. Okay, done. Let's test it. And it works. Great. All right, serial input. And I tell you, this is really cool. So what serial input enables us to do is to send data from another machine to our kernel. And that means, for example, that we can type something on the keyboard here, send it to our kernel, and the kernel then can process it. So we theoretically could remote control our kernel with that. And input works in much the same way as output. First, we have to check whether the connection is ready to read data. And to do this, we have to check the line status register, but this time we are interested in the value of bit 0. If this bit is set to 1, there is data that can be read. Then, as usual, we use the data register to access the data. But this time, we use the in instruction, because from the perspective of the kernel, we want to read data. Alright, let's implement that in C. First, we write an if statement to test whether there is data to be read, and then we call the in instruction and we store the read value into a variable. And to see what we have read, let's print the value to the screen. And because this only would read data once, and we'd likely miss the exact moment when the data arrives, we put that into a loop. And by the way, this is a somewhat weird way of implementing that, but for demonstration purposes it's fine, and we'll fix that in a minute. Alright, let's start our kernel and test it. And to test the input, we only have to type something into the terminal. Okay, how cool is that? That's, I don't know, so nice. Okay then, let's put that into some proper functions. First, we write a function that checks whether there's data to read. Then we write a read function. And once called, this function waits until there's data to read and then reads it. And this type of repeatedly checking is what we mean by a polling approach. Now, let's add the function declarations to the header file, and then let's write a nice little test that lets us input multiple letters. So this loop repeatedly reads input and then prints the input to the screen. And this way we get a kind of remote control. I mean, kind of, because it cannot do anything real right now, but we get the picture of where we're heading. Now, let's test it and take a look.
Alright, that's pretty cool, isn't it? Now, for the final part, let's get back to the router. The router is obviously running some kind of kernel. And what we do now is to get a shell there. And some people call this hacking. I don't know. Maybe it is, maybe it's not. Frankly, I don't care what it's called. In the end, we'll just use a UART connection to get a shell. And that's in and of itself a neat trick. So let's do it.
So, to get a shell into the router's kernel, we use this device. And what this does is to send the UART data via USB to our computer and vice versa. And as you can see here, it has the exact same pins that we've seen on the router. And to connect them, we just wire it up like this. Okay then, so this end has to be connected to the router like this. And we could definitely solder it now, but my soldering skills are as impressive as the average TikToker's attention span. So I redneck engineer it with this piece of wire. And you have to admit, this looks also great, doesn't it? Now, let's connect it and fire up a Kali machine. In Kali, we first have to check whether the device is recognized. And that looks good, here it is. And then we check which TTY the device was assigned to, and here it's on TTY USB 0, and let's keep that in mind for later. Okay then, now we start Minicom. And Minicom is a text-based terminal emulator that is used for serial communication with IoT devices like our router. So let's start it and check the settings. And here we can set all kinds of stuff that defines our connection. So right now it's set to a baud rate of 115,200 and a frame layout of 8Nun1. Okay, that's all we need to know. Let's exit that. The thing is, to get a working connection, we have to guess the right connection settings. And 8Nun1 as a frame layout is pretty common, so we'll stick with that. And as our baud rate, let's just randomly try 57,600. So we hit return and now Minicom is running. And then we have to plug in the router. And yes, that's the level of tidiness I've chosen to live in. Don't judge, my friends. And we get gibberish. Yeah, not good. So something went wrong. And most likely we guessed some of the connection settings wrong. So let's try another baud rate. And this time let's choose 115,200. And we hit return again. And Minicom is running. Then let's plug in the router. And now, unbelievable, we get something. That's actual readable text. So we have a UART connection to the router. I mean, how cool is that? That's pretty amazing. And it gets wilder. So if we press return a few times, we'll see that we have a root shell. So we can browse the file system. See? And even more, we have some tools installed on here. So for example, we can cat files and look at the content, like this HTML file here. So that's on here because the router runs an HTTP server for the router's config page. But we also hit some barriers. For example, for the most part, this is read-only. So if we want to create a folder, it fails. But still, there are places on here where we can do that. But that's a topic for another video. So why is this possible? Well, this is just the way for the engineers who built this to get some logs and so on. And in our kernel, we laid the foundation to do that too, which is pretty cool.
That's it for today. Stay sane, my friends.